Hello everyone! In this video, I will create a simple shader for generating an animated star using a noise texture. And as usual, we will have plenty of parameters available to customize this effect to suit the needs of our game. So let's get started. And just like last week, we won't apply the effect to an existing image. Instead, we'll generate it entirely on a black background. So I'll create a new scene and set everything up for this kind of shader. Okay, right-clicking the scenes folder, create a new scene. It's a user interface. Let's call it noise star. Okay, and right-clicking the root node, add child node and colorect. In the inspector, I'll change the color to black, expand layout, transform, and set the size to Full HD, which is 1920 by 1080. Okay, and scrolling down to the materials section, creating a new shader material, click it and create a new shader, type shader, mode canvas item, and the path is shaders / noise star .gd shader, and creating and clicking again to open it in the shader editor. And as always, I'll delete everything from the generated code that we won't need for our effect, leaving only the fragment function, deleting vertex and deleting white. Control S to save. Okay, so we want to create a circular object that maintains its shape regardless of the dimensions of the element it's contained in, so this colorect, which means I'll start with a uniform parameter defining the resolution. And let's put it to the uniform parameter section at the top, uniform vec2 resolution equals vec2 and our Full HD resolution, so 1920 and 1080. Okay, this is the default value. Besides that, we know that the star should exhibit certain fluctuations to create the impression of thermonuclear reactions taking place within it. We'll handle this with animation, which requires a parameter that determines its speed. Uniform float speed with a hint range, and it starts at, let's say, 0.2, and the speed range goes from 0 to 1 with a step 0.01. And as I mentioned at the beginning, the effect is based on a noise texture, so I'll add the corresponding parameter. Uniform sampler 2D, let's call it noise underscore text, and the hint would be repeat enable, because we want to stretch it over the whole area regardless of its dimensions. Very well. Now let's jump into the fragment function, where I'll write a few basic lines of code. I'll shift the coordinates origin to the center, recalculate the aspect ratio, and define a time variable based on the internal time and the speed parameter. Let's do it right here. I'm deleting the comment, and now vec2 uv equals uv minus 0.5, moving the origin of the coordinates to the center. Next, we need to recalculate the aspect ratio, so uvx is multiplied by resolution.x divided by resolution.y. Perfect. And finally, the time, float time, is time times speed, and I think it will be still too fast, so let's divide by 10, multiplying by 0.1. Okay, as you may remember from previous tutorials, it's often useful to use polar coordinates when working with circular objects. I once made a dedicated video on this topic, so if you're not very familiar with polar coordinates, I definitely recommend watching it. You'll find the link in the description of this video. So, for polar coordinates, we need the angle and the distance from the origin. We can calculate the angle using the tan function. Let's do it here. Sorry, scrolling down the code. Float angle equals tan of uv.x and uv.y. Okay, as for the radius, we'll actually use it to sample a value from the noise texture at the given angle, so we can create a uniform parameter for it, which I'll call shift. Let's do it here. Uniform float shift with a hint range, and it starts at, let's say, 0.3. And the range again is from 0 to 1 because we are working with normalized UV coordinates, so this is how it looks, and the step point 0, 1. Okay, so I'll go back to the fragment function and define a vector called polar that combines these values together. We'll also add time-based variation to both components of the vector, which will produce the animation we mentioned earlier. So vec2 polar is vec2, and it's composed of angle times pi divided by 2, and the second component is shift, and let's add the time variable. Okay, as we can see, I multiplied the angle by half of pi, so the resulting effect loops smoothly after completing a full rotation around the circle. And to make the star's radiation decrease with distance from the center, we'll include that factor as well. So another parameter will come in handy here, which I'll call size. So scrolling up to the parameter section and a uniform float size with another hint range, and the size will start at 0.3 again, and this time it goes from 0 to, let's say, 10 with the step point 0, 1. Alright, now I'll insert the corresponding line of code in the fragment function, so going to the end of the function, and float dist for distance is the length function applied on UV divided by size, sorry. Okay, at this point, we have everything we need for the first version of the star. So now we'll sample a pixel from the noise texture and divide the result by the value of dist, like this. So the output, color in capital letters, which is simply the result of the texture function applied on the noise texture and our new polar coordinates, and dividing the result by the dist value. Wait for it. Okay, something is here. Actually, the result isn't very impressive because I forgot to create the noise texture. The parameter, if I expand this, shader parameters, the parameter is still empty. So I'll assign a new noise texture 2D from this list to it. Okay, we are almost there, but not totally. What we need now is to click this parameter. Let me just expand the column a little bit so we see more of that. And here in the noise parameter, let's create a new fast noise light. And let's make the texture seamless. Okay, that's much better. I think we can try adjusting the parameters and see how they affect the look of the effect. So let's just, where are we? Here, shift. If I change the shift, we can see that the noise texture is sampled at different radius of the polar coordinates, so it's a little bit modified. And as for size, yeah, now it's bigger, now it's smaller. We can simulate something like an explosion, maybe. Okay. Very well. However, this star is still far from perfect. First of all, we want it to have some color, so add a parameter called color, which will be a vector 3 representing an RGB color. Again, I'm scrolling up to the uniform parameter section and adding the mentioned parameter uniform vec. Yeah, I said vec3, but let's make it vec4 actually, because it will be better usable at the end when we multiply the result of the texture function with that, which is a vector 4 too. So the hint is source color, which, as you may remember from previous videos, adds a color picker to the inspector, to the shader parameter section, and let's put default value into that, and I think the best one was something like 0.5, 0.3, 0.1 RGB, and the alpha is 1. Okay, and now I'll multiply the resulting pixel by it, scrolling down, and here I'll simply add color times texture function. Okay, that's not bad. But what we can see that the pixels at the edges are transparent. So the result might look better if we place a black background underneath. So I'll add another color rect to the scene, going back to the scene panel and right-clicking, add child node, another color rect, and I'll put it just before this first one, change the color to black, and change the dimensions layout transform to Full HD as well, 1920 by 1080. That's much better. Let's click back to the original color rect, which contains our shader. Okay, but yeah, sometimes we might want to shorten the length of the rays coming out of the star. So I'll add a parameter called mask. And once again, I'm scrolling up to the uniform parameters section and adding one more parameter, uniform float mask, with a hint range, and the initial value I'll set to 0.5. And the mask goes from 0 to 1 with the step 0.01 again. Okay, scrolling back to the fragment function, and just before the last line, I'll add the mask definition. All right, and we'll use a smooth step function for that and subtract it from 1 so that we remove the edges rather than the center. Okay, so let's call it simply m. Float m is, as I said, 1 minus smooth step applied on the mask value and mask plus, let's say, 0.5. These are the edges, and we apply that on the length. Sorry. Yeah, of UV. All right. So this is the mask definition, and then I'll simply multiply the resulting color by the value of m. Okay, here we go. So we can try adjusting the mask in the inspector, scrolling down, and here it is. So if I increase, nothing happened too much, but now when I decrease that, we can see how the image is cut, and the rays are definitely shorter. All right, and if it doesn't feel like the cutoff is strong enough, like if I just change it to 0, but it's still too big, we could lower the value of 0.5 in this code, or even turn it into another parameter, but that's something everyone can easily do on their own. Let's just reset to 0.5. Okay, there is one more parameter that will represent something like the age of the star. Even though that's a very simplified concept, I'm basing this on the idea that a star like our sun gradually expands until it becomes a red giant, and then it likely explodes. We won't go that far in this shader, but we can simulate some growth. So we'll add a parameter, I think this is the last one, called age. Okay, so uniform float age with a hint range, and the initial age I think we set to 1, which means the current status. And let's set the range from 0 to 1, again with a step point 0, 1. Okay, scrolling back down to the end of the fragment function, and let's fix the last line so everything stays as it is except this part. Instead of dividing by this, I'll divide by the power function, this to the power of the h, so po dist and h. Okay, and now nothing happened, of course, because h is default value is 1, and everything to the power of 1 is just the initial value. But now let's increase the h, and we can see how the star grows and becomes brighter. So let's say this is something we can use to simulate exactly, not exactly, but very roughly, this kind of effect, and something like happens to the star. Okay, and with that, we've covered everything I wanted to show today. Thank you very much for watching. This is a very simple effect that doesn't consider details like simulating the surface of a star, sunspots, various energy outbursts, and so on. On the other hand, the computation is very fast and should have virtually no impact on game performance, even if we place several of these stars in a scene at once. And as always, I'll add the final shader to my Godot shader pack product. For now, take care, best luck with your projects, and I'll see you in the next video.